So here we have a diatomic molecule that's rotating. And then note that this is something we saw a little bit in 7a, the idea of a diatomic molecule, presumably in a gas, and that molecule is rotating. And we looked briefly in 7a at the idea that it can't have just absolutely any value of energy. It can only have certain specific values of energy, or at least there's a minimum, lowest possible energy value. And now we're looking at the actual values for energy it can have. It looks like the possible values of energy are B times L plus 1, where L is a non-negative integer. So any positive whole number, also including 0, I think. So L could be 0 since it just says it's non-negative. So that means that rotational energy is quantized. There's only certain specific values. In fact, it might be a good idea to list out some of these possible values. We could have, for instance, E sub 0. If you plug in 0 for L, what do you get? Yeah, that's just going to be 0. So 0 is one possible energy value. It is possible for the atom to have, or the molecule to have 0 rotational energy. Or if we plug in 1, what do you get if you plug in 1 for L? Yeah, 2B. What if you plug in 2 for E? Yeah, you plug in 2. Actually, wait, if you plug in 2 for L, yeah, we get B times 2 times L plus 1, which would be 3. So yeah, that's going to be 6B. And then you plug in 3 for L, what do you get? Yeah, 12B. Let's go ahead and get E4 also. B times 4 plus 1. Looks like that's going to be 20B, right? So we get this, this list, and we can continue this list as far as we need to of energy values. And notice that these are not evenly spaced. It's possible to be all the way down at 0 energy. The next level up would be 2, then 6, then 12, then 20. So we're increasing by plus 2B, plus 4B, plus 6B, plus 8B. So these are getting, we start with a small energy gap, then larger and larger and larger gaps between these energy bands. In fact, we could even draw this out if we use our usual sort of diagram for this. We got a small gap, and then a larger gap, and then a larger gap, and then an even larger gap. I'm not really drawing this to scale, but just a general idea of the energy bands getting further and further apart. So let me draw that out. So we've got these possible energy levels at 0, at 2B, at 6B, 12B, 20B, and so on. So these bands represent possible energy levels. Any questions on that so far? So in part A, it's saying we've got a particular diatomic molecule that's in a rotational state that's not the ground state. And it doesn't specify which one it is, but let's just say, let's assume it's in states, I don't know, maybe state 3. So let's say right now it's in state 3. And we can consider the possibilities of a photon absorbed for it to transition up to the next state, L plus 1, or the wavelength of a photon emitted when it transitions to the next state down from L to L minus 1. And just from the diagram we've just drawn, what do you notice about the transition up to the next energy state versus the transition down to the next energy state? What's different about those? Yeah, the transition up is a lot more energy. Is that just coincidentally true for n equals or L equals 3, or does that work for other values as well? Yeah, it looks like that's true for all of these. For instance, if you take a look at L equals 2, going up takes a lot of energy. Going down means you're losing only a little bit of energy. Or if you're starting at L equals 1, going up takes a lot of energy. Going down loses only a little bit of energy. So it seems to be true for at least all the cases we see here. And based on the fact that we're multiplying by larger and larger numbers, the L times L plus 1, these gaps are just going to keep getting larger and larger as we go further up. Any questions on that so far? So it looks like we can gain lots of energy, or we can lose a little bit of energy. And how does an atom gain energy or lose energy? Or a molecule, I should say. Yeah, photons. You can gain energy by absorbing a photon. Or you can lose energy by emitting a photon. And presumably that means you'd be absorbing a high energy photon or emitting a low energy photon. But how does the energy of a photon, because it's asking about the wavelength of the photon. So how does the energy of a wavelength compare, or energy of a photon compare to the wavelength of that photon? Do we have any formulas comparing wavelength and energy? Yeah, we can use hc over lambda here. If we just write out our usual formula that energy of one photon equals h times c over lambda. So if you're absorbing a high energy photon, high energy tells you what about the wavelength? Yeah, it's going to have a very small wavelength. And meanwhile, the low energy photon, what does that tell you? Right, that's going to have a large wavelength. So it looks like those are the options. If you're in any specific energy state, you can gain energy, go up to the next level by absorbing a small wavelength high energy photon, or you can lose a little bit of energy by emitting a low energy photon, which is going to have a large wavelength. So it looks like those are the possibilities. Absorb a short wavelength photon or emit a long wavelength photon. Any questions on that so far? And then it looks like in part B, it's asking for some actual numerical calculations specific to oxygen gas. So let's see if we can run the calculations here and plug in the actual numbers. It might be more useful in a case like this to run the calculations with variables, and then we can fill in numbers at the very end. We're specifically going from state 2 to state 3. So that's going to look like I think that will be from 2 to 3, that's this transition. So the transition from 2 to 3 what would you say about the change in energy there? How much energy is it gaining? It's going from where to where here? If you take a look at the initial energy and final energy, yeah, it looks like 6B. Because if you calculate delta energy, you can write delta energy as usual as final minus initial. Looks like we're starting in state 2, which is 6B, and we end up in state 3, which is 12B. So 12B minus 6B is positive 6B. So that means to go from state 2 to state 3, you are gaining 6B energy. So that's the change in energy for the system. And in general, for any quantum system, the change in energy for the system equals plus or minus energy of 1 photon. We now know change in energy for the system is plus 6B. We can set that equal to energy of 1 photon, hc over lambda. And that's lambda is specifically the wavelength of the photon, of the light itself. And we want to know what's the wavelength associated with this. So how would we isolate lambda here? Yeah, hc over 6b. So that's our formula for the wavelength. This is the expression for the wavelength that will be absorbed because we're going up in energy state. We're gaining energy. And we can fill in some values there. What's our usual standard value for hc? Yeah, 1240 with units of electron volt nanometers. And that's going to work well with the fact that B is also described in nanometers. We're going to have 6 times B, which in this case is 1.8 times 10 to the negative 4. So we've got dividing by 10 to the negative 4 is the same as multiplying by 10 to the positive 4. So 10 to the 4, which is just 10,000. Electron volts cancel out. We'll be left with nanometers, and we've got 1240 divided by 6 times 1.8, which is that just 9 point something? 9.2, I think. Calculator for that. Oh, 10.8. And then we're going to divide 1240 by that value, 1240 divided by 10.8. And we get about 114. Times 10,000. I think that should work. Yeah, that looks about right. Any questions on the numbers there so far?
Is this like a okay value? Because like it seems like it's a very, very high number.
Yeah, this is very large. We got 1,148,000. So that's over 1 million nanometers. So that is a very long wavelength, way longer than visible light. So that tells us this is definitely not visible light. The wavelength is way too large for that. So this is going to be beyond visible light. This is going to be some sort of longer wavelength. And longer wavelength means a much lower energy per photon. And I think that corresponds to the idea that 10 to the negative 4 electron volts is an extremely small amount of energy. I mean, the energies we were dealing with, if we were looking, for instance, at the energy levels of a hydrogen atom, for instance, those were more along the lines of 5 to 10 electron volts, using the negative 13.6 electron volts as a standard. So 10 to the negative 4 electron volts is an extremely small amount of energy. And an extremely small energy would correspond to a very long wavelength. Any questions on that so far? That almost makes me wonder if that might be an error in the numbers in the problem itself, because that's an absurdly small amount of energy. But if that's accurate, this would be the wavelength associated with that transition. And yeah, part C on this one, I think, is largely comparing this to the stuff we saw in 7A, that the idea of modes being frozen out, that the energy, I mean, we've been looking at the energy that's required to get it to transition from one energy level to the next. But in order to figure out, does it even have that much energy? The energy that's available is this 1/2 kBT, the energy per mode we were looking at way back in 7A. So the question is, if we're at a certain temperature, let's say room temperature, we could just plug in 300 Kelvin for temperature and figure out how much energy is available and compare that to the amount of energy we need to jump from one energy level to the next. Because if the energy is too low, we'd be stuck at ground state, no rotation at all. To start rotating at all, you need to bump it up to 2B. Anything lower than 2B, and it can't exist in that in-between region. So it would just stay as the not rotating. So we could compare that. If you plug in 300 Kelvin for T, you'd have 1/2 times 300 Kelvin times 8.62 times 10 to the negative 5th. That would tell you the available energy. One half kBT is 1/2 times 8.62 times 10 to the negative 5th times 300. And that will be in electron volts because the kelvins cancel out. So 1/2 times 8.62 times 300 divided by 10 to the 5th is about 1/100th. Yeah. So that means we've got about 0.01 electron volts worth of energy available. How does that compare to the energy that's needed to bump the oxygen atom up to the next level? If you're going from the very lowest energy state, and zero energy, up to the very first excited state, how much energy is that? Yeah, you've got to add 2B. So the energy required to start rotating in the first place would be E final minus E initial, which would be, assuming we end in state 1 and we started at not rotating at all, that'd be 2B. And for oxygen, we're using, what was it, 6 times 8.62 times 10 to the negative 5. Electron volts, and then we'll have to multiply that by 2 because it's 2B. So about 17 times 10 to the negative 5, or 1.7 times 10 to the negative 4. So that means to get this rotating in the first place, you need about 2 times 10 to the negative 4 electron volts, 0.0002. The energy we have available at room temperature is about 0.01 electron volts. Do we have enough energy to get this rotating? how does the energy we have available compare to the energy we need? Yeah, looks like the energy available, 10 to the negative 2 electron volts, that's almost 100, well, it's about 50 or so times as much as the energy we need. Because we've got about 0.01 versus we got about 0.0002. So the energy available is way more than the energy needed to make it rotate. That means it will be able to rotate. So at room temperature, we can assume that the rotational modes are active. The oxygen molecules can rotate and will rotate if the temperature is around 300 Kelvin. In fact, they would have to be much lower energy much lower temperature in order to not be able to rotate. If the energy per mode is less than the energy required to get to the first excited state, you can assume that everything's in the ground state. But if the energy available per mode is way more than that, you can assume that everything's rotating. Any other questions on that one? Okay, any other quantum mechanics examples you'd like to work on? Or any other topics you'd like to talk about? Yeah, do you have any standing wave examples you'd like to try out? You sent me a couple of standing wave problems this morning also. Did you want to try any of those from those practice quizzes? Looks like there was the one about the violin and the one about the Olefonts horn. And while we're at it, let's take a quick look at those, the formulas for various energy systems. Notice that there's these three formulas listed here, in addition to the one we were just looking at, the B times L plus 1. This is what I was saying earlier about how there's various different formulas you can use for energy of the system. Which one you would use really just depends on which type of system you're talking about. Okay. For example, this h squared n squared over 8 ml squared. What sort of system is that describing? When would you be using a formula like that? Under what sort of circumstances? Yeah, that's the particle in a box model. Specifically a particle in a one-dimensional box, essentially a long, narrow pipe. So this is usually we think of it as an electron, but it could be any particle in a long, narrow tube, basically. And this goes back to the idea that the particle also acts like a wave. So a particle in this confined space is going to act like a one-dimensional standing wave, very much like the standing waves in strings or pipes that we were looking at earlier. So the particle itself is going to have wavelengths equal to 2 times the length of the pipe divided by n, just like the standing waves on strings we were looking at. But if you convert that wavelength to a momentum using the de Broglie equation, and then convert the momentum to kinetic energy, these are the values you get. So these are the energies of the particle in the box associated with standing waves. And as usual, you would look at differences between starting energy and ending energy and say that change in energy equals the energy of one photon that's absorbed or emitted. What about this other one, this negative 13.6 z squared over n squared? When would you use that one? Or what sort of system is that talking about? Yeah, that's the hydrogen, like generally any atom that is small enough and has only one electron, it can be treated as acting like hydrogen. And for hydrogen atoms, this formula works perfectly. For anything that's close enough to hydrogen, this is a reasonable approximation. And the more like hydrogen the atom is, the better an approximation this is going to be. But yeah, anytime you're dealing with energy levels of just one atom with one electron involved, then this formula tells you the energy of the atom with the electron. And that kind of combines the potential energy of the interactions between the electron and the nucleus and the kinetic energies, or equivalent to that. Z being the atomic number, the number of protons in the nucleus, and N being any positive whole number, 1, 2, 3, etc. It can't be 0, of course, because division by 0 doesn't make sense.
So for this, we can use it for any like hydrogen atom, and so Z doesn't always have to be 1, right?
Right. If it is hydrogen, then of course Z is going to be 1. If you're dealing with, let's say, a helium ion, then Z would be 2, or a lithium ion, Z would be 3, or an oxygen ion, Z would be 8. So Z is just the atomic number of the ion you're talking about. And when you draw out that chart of energy levels, it's still going to be the same basic pattern, the same idea of a big gap, then a smaller gap, and a smaller gap, and a smaller gap. It's just that the spacing between gaps is proportional to Z squared. Because if you work it out with Z equals 1, you get a certain pattern of values. If you replace Z with 5, 5 squared is 25, so all those values just get rescaled. They get multiplied by 25, which also means all the gaps get 25 times bigger. So all of the absorbed or emitted photons become 25 times more energy required, which means all of the wavelengths become 1/25 as much. But again, the formula for the energy of the system depends on which system you're talking about. The formula for the energy of a photon is always going to be hc over lambda, because that doesn't depend on the system. And what about this third equation here, the 2 epsilon 0 times n plus 1/2? What sort of system is that describing? Yeah, that's any quantum oscillator. So basically anything that acts like connected by a spring, such as 2 bonded particles that are oscillating back and forth, attracting and repelling each other. And again, this is just describing what energy levels are permitted. Where n, I think in this case, n is allowed to be 0. So n is 0, 1, 2, 3, etc. And a convenient shortcut for this, it's usually written as this obscure looking 2 times E0 times n plus 1/2. But a more convenient way to write that, if you distribute the 2 to the n and the 1/2, you could also write this as E sub n equals E sub 0 times 2n plus 1 from the 2 times n and 2 times 1/2. And what sort of a number is 2n plus 1? Yeah, that's just going to be any odd number. So I often find it useful to think of this as just E sub n equals E sub 0 times some odd number, where n equal, or state 0 would be using 1 for the odd number, state 1 would be using 3 for the odd number, state 2 would be using 5 for the odd number, state 4 would be using 7, and so on. So it is useful to still use the 2n plus 1 so that n actually means something. But what you actually get is just this baseline value, the lowest possible value, times any odd number. So this value and 3 times that value, 5 times that value, 7 times that value, 9 times that value are the possible energy states. And what would you expect about if we draw out that usual chart, that the energy grid? What do you notice about 1e, 3e, 5e, 7e, 9e? How are those spaced out? Yeah, those are equally spaced. This is one of the most important defining attributes of any type of quantum energy system, really. You want to look at how the energy values are spaced out. For the quantum oscillator, they're equally spaced. Each gap is the same size as its neighbors. For the hydrogen-like atom, you start with a big gap, then get smaller and smaller and smaller gaps as you go up. For the particle in a box, it's proportional to n squared. So the first gap is going to be small, then bigger, then bigger, then bigger. And the rotating one we were looking at in the previous problem, the b times L plus 1, that also got bigger and bigger gaps as you go up. So that's a very important thing to consider for any of these quantum systems. You want to investigate usually using one of those diagrams of energy levels. As you go up that line, are the energy gaps getting bigger and bigger, or smaller and smaller, or are they equally spaced? Or is there some other pattern of, I don't know, alternating values or something? But that pattern of are the gaps getting bigger or smaller or staying the same is really what determines what the absorption spectrum and emission spectrum really look like for that system. What type of photons can they emit? What type of photons can they absorb? So a very important thing to keep in mind there. Any other questions on the quantum energy level stuff? All right, then let me pull up that other example that you sent. This is the one with the Olefonts horn. So here we have, we've got a horn that acts like a pipe that's open at one end and closed on the other. So let's sketch that out. Just as a general idea, this is going to look something like this. A pipe that's open at one end and closed on the other. And we know the length. We know the length is 85 centimeters. Now let me make that 0.85 meters, because I think meters is going to be more useful here. And we want to produce standing waves here. And blow the horn so forcefully that he excites a standing wave with 5 nodes. And we want to know the frequency. So in a case like this, if we've got this, this sort of mixed pipe where we've got an open end and a closed end, what do we know about what's happening at those ends? What sort of point would we expect to see at the open end versus the closed end? Yeah, they've got to be opposite types of endpoints. So let's say we've got a node at the closed end and an antinode at the open end. So node at the closed end, and an antinode at the open end. Let me actually make this a little longer. I think we're going to need some more space here to draw this well. And it specifically says we want a standing wave with 5 nodes. So we're going to need 5 more nodes here. And nodes and antinodes are going to be alternating. So we're going to have to go from node to antinode to node to antinode, node to antinode, node, antinode, and so on. So if we want to fill these in, we're going to need a total of 5 nodes. We've already got 1, so we just need 4 more. Those should be equally spaced. I might need to modify that a little bit. Something like that. And then between those nodes, we should expect antinodes, also equally spaced. And this might not be exactly to scale, but it should get a good general idea of what this looks like. So that's a standing wave with 5 nodes, as described here. And it starts at a node and ends at an antinode because we have different types of endpoints here, open at one end, closed on the other. And we can connect those to actually try sketching out what this wave looks like. And again, this is not necessarily to scale, but it should give us a good general idea of the shape of the wave. So there's our standing wave. Any questions on that so far? And if we want to compare the wavelength to the length of the pipe itself, if you're dealing with this type of pipe that's open in one end and closed on the other, or if you're dealing with like a vibrating rod that's fixed in place in one end but free to vibrate on the other, instead of counting half wavelengths, I find it useful to count quarter wavelengths. Quarter wavelength would be, for instance, from antinode to node. There's a quarter wavelength, in the sense that if we take a look at the usual shape of a wave, there's one full wavelength. If you go from node to antinode, that's a quarter wavelength. Or antinode to node, that's a quarter wavelength. Or node to antinode, that's a quarter wavelength. Antinode to node, that's a quarter wavelength. So we can count quarter wavelengths specifically because we're starting at a node and ending at an antinode. What does that tell you about the number of quarter wavelengths if we're starting at one type of point and going to the opposite type of point? Yeah, that's one way to look at it. 2 lambda, or it doesn't necessarily have to be 2 lambda necessarily, because we don't have to have an even number of waves plus an extra quarter. I would generally think of it as if you have, like if we actually count up the quarter wavelengths here, we got 1, 2, 3, yeah, let me fix that. So counting quarter wavelengths, I'll just alternate red and white here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. What's important about that 9 quarter wavelengths? Why is 9 so important here as a number of quarter wavelengths? That does equal the length. What if it had been 10 quarter wavelengths? Would that still work? If we extended this for an extra quarter wavelength, would that still work? Yeah, the problem is that would end at a node. And generally, this is all about odd versus even. If you have an odd number of quarter wavelengths, then one end is a node, the other end's an antinode. If you had an even number of quarter wavelengths, like if we extend this to 10 quarter wavelengths, then both ends would be nodes or both ends would be antinodes. And that can't happen in this particular pipe. So in general, if you have opposite types of endpoints, then the length of the pipe has to be an odd number of quarter wavelengths. So that's really the key here. We've got to have an odd number of quarter wavelengths. If you had fixed or free, like if both ends were open or both ends were closed, then you would have an even number of quarter wavelengths, which just reduces to some lambda over 2. So we know that the length has to equal odd number times lambda over 4. If you solve that for lambda, what do you get? Yeah, 4 times L over an odd number. So those are the possible wavelengths you can get. all the wavelengths you can get from this type of pipe, open at one end, close at the other, all fit into the form 4 times the length of the pipe divided by some odd number. Those odd numbers being 1, 3, 5, 7, etc. Also, instead of the wavelength, we really want the frequency. So how do you convert wavelength to frequency? How are frequency and wavelength related to each other? What do you get if you multiply those? Yeah, that gets you speed. Speed is frequency times wavelength. So frequency is just going to be speed over wavelength. That means since we're dividing by wavelength, we're just multiplying by the reciprocal. So V times an odd number divided by 4L. So we can find the frequencies that are allowed here just by multiplying speed times any odd number divided by 4L. In this case, what odd number would we use? Yeah, we're specifically looking at a standing wave with 9 quarter wavelengths. So we'd use speed times 9 divided by 4L. And we could even fill in those values. We know the speed of sound in air is 340 meters per second, as usual, or as given. We know that the length of the pipe is 0.85 meters. Meters and meters cancel out. We're going to be left with 1 over seconds, also known as hertz. So 340 times 9 divided by 4 times 0.85. And I'm getting about 900. Actually, exactly 900. So that's the note that this is going to produce. The frequency is 900 hertz. Any questions on that? All right, then looks like that's it for today. Let me know if you have any questions. Feel free to email me, and I will see you next time. You're welcome.